Okay, 5.8 is analyzing graphs of polynomial functions, and 5.9 kind of goes with creating graphs off of looking at, or creating equations off of graphs. Okay. So, we have lots of things that we've kind of talked about, and we're piecing them all together, okay? F of x can be represented by anything that goes, any type of polynomial function starting with any power. All it's saying is that it works its powers down until it becomes without a power and it's just a constant. The 0, k, is a 0 of the polynomial function. X minus k is a factor of a polynomial function. K is a solution of a polynomial equation. These are all things we've done. And the x-intercepts, if k is a real number, k is an x-intercept of the graph of a polynomial function, and it passes through it. When does it bounce?
When it's even.
Yes, and so it's going to pass through when it's not. Okay, so it says use x-intercepts to graph a polynomial function. Okay, so we want to graph this function. How would I graph this function? What would I start with first?
The x pieces.
Okay, the x pieces. So if I start with the x pieces, I know x equals -3 and I know x equals 2. Yes?
Yeah.
Okay, because I would set each of those segments equal to 0 and solve, and I would get that. So I know at one point, here's the problem though. Okay? Let's say I go to graph this. Okay, so I'm going to graph this. I'm going to graph x plus 3, which is actually x equals -3. I know that's a point. And I know x equals 2 is a point. On those, do you know if they're bouncing or passing through them?
Passing through. Bouncing, actually. Bouncing.
Well,
Wait.
Bouncing. Very much.
One would be doing one of them.
yes, one would be doing one and
The
one.
negative bounces, the positive goes through. Or is it
So which one goes
I
through?
think the positive bounces the negative.
Well, yeah, the -3 is going through because it has an odd power. It has a 1 up there, right? Okay? The 2 is going to bounce and shift away. Okay? So I can kind of take a look at what my graph's going to look like. I know it's going to pass through here somehow, and I know it's either going to bounce up like this or it's going to bounce down depending on where the graph is. Is the graph facing up or down, technically speaking? Up. So it's probably going to pass through here and bounce that way.
That's why.
Okay, you can start to think that through. Now, the good news is this. To graph the rest of this, you just plug in points and do math. Okay, so let's plug in -2, -1, 0, 1, and 3, because I'm trying to take numbers that are around these points. Okay, -2, -1, 0, 1, and 3. Does that make sense? -2, -1, 0, 1. We're going to plug these points in and we're going to figure out what the outputs are in graph. If I plug in a -2, okay, if you plug a -2 in that equation, you have -2 plus 3, which is 1. You have -2 minus 2, which is 4, -4. -4 squared is 16. 16 times 1 is 1. And then you have 16 times 1, 6. What is 16 times 1, 6?
16 times 1, 6.
Mm-hmm.
I don't even know. I ain't got a
8/3.
Yeah, 8/3. 2 and 2/3, so 8/3.
Mixed number time.
Okay? So I'm going to graph -2, and then I'm going to graph 2 and 2/3, like something around there.
Texting people?
Okay? Now I plug -1 in. -1 plus 3 is 2. -1 minus 2 is -3. What's -3 squared?
9.
9 times 2 is 18. 18 times 1, 6 is what? What's 18 divided by 6?
3.
3.
I'm smart.
Does it matter what points you
Hey,
put
I did
in?
not get the answer off
You
so
want
I
to
don't know
plug
what you're
points
talking
that
about.
are around the points that you graphed.
I just
Does that make
slightly
sense?
answered it after
Plug in
you
a 0, so you get 3 times -2 squared. What's -2 squared? 4. 4 times 3 is 12. 12 times 1, 6, or 12 divided by 6 is
2.
2.
See, now I'm smart. See, now I'm smart.
Okay? And then
Really want to remember?
plug in a 1. 1 plus 3 is 4. 1 minus 2 is 1, 1 squared is 1, 1 times 4 is 4. 4 times 1/6 is what?
2/3.
2/3.
They're ultimately doing too much.
So 1 and 2/3. And then we have the 2, and then we plug in a 3. 3 plus 3 is 9. 3 minus 2 is 1. 1 squared is 1. 1 times 9 is 9. So you get 9. What?
That ain't hard at all.
You get 1.
That's crazy. I thought it was gonna be so
Oh,
hard.
because I said, I multiplied, yes,
Oh,
okay,
no,
I'm
no.
being stupid, that's fine. So 3 and 1.
Really easy.
So then I just come through here and we bounced off of 2 like you said, and we go through 3 and through -3. And there you have a graph. Can you handle doing that?
Yeah, that's easy.
Okay, so start, well, you have to show that it goes through that point and then you have to show that you're bouncing. Yes, Isabel?
For the first point, did you just do like basically just do 8 divided by 3 and like rounded it?
Yes.
To,
Yeah. It's like it comes out as 2.6 or something, so 2 2/3, yep. Okay, so do you think you can handle graphing those and figuring that out by hand? Okay, you won't have super large ones. I'll try to keep you away from super large ones so that you don't have to graph like massive numbers and things like that. Okay, then we need to talk about turning points, okay? So, turning points. Another important characteristic of graphs of polynomial functions is that they have turning points corresponding to the local maximum and minimum values, okay? Anything that's maximum is where it's like heading down on a roller coaster, and anything that's minimum is like my little loop coming back up, okay? So you have maximum points and you have minimum. The y-coordinate of the turning point is the maximum of the function. The y-coordinate is the maximum, okay, of the function. The y-coordinate of the turning point is the minimum. So you're looking at what the y value is. If you can find what the y value is, that's your turning point. That's your maximum or your minimum. So when it asks for what the maximum or minimum is, it's not asking for a set of points. It's asking for what the y factor is, okay?
So the max.
Because it's, think about it, it's your height and your like lowest point, your highest point and your lowest point. That's the y-axis, okay? The graph of every polynomial function of degree n has at most n minus 1 turning points. So if I have a degree of 3, I have up to 2 turning points, okay? But I might only have 1. I have up to 2. If I have a degree of 6, how many turning points could I have? 5. Does that make sense? Okay? So, they want to know, so that was all of 5.8 that we're doing, just those 2 little things. 5.9 now is taking functions and creating equations off of them. Okay? Creating equations off of them. So here it says, write the cubic function whose graph is shown. So, cubic means what power is going to be the highest power that I have? 3. Okay? And we already see that we have 1 point here that it crosses through the x, or the y-axis here, the x and the x there. I can start to create some things off of that, okay? The first thing you need to look for is this when you're creating a graph. You need to use the given x-intercepts to write in factored form. So what are my x-intercepts here?
4, 3, and 1.
-4, 1, and 3.
Yeah.
How do you write those into,
X plus 4, X minus 1.
Good,
X minus
okay.
4.
so my equation is going to say this. Remember when we do equations, they always have that a in front of them because we don't know if there's a fraction there or not, okay? And then in this case we have x plus 4, we have x minus 1, and we have x minus 3. What do you think I'm going to do next?
I think you're going to plug in something for y. Maybe
I
-6.
am going to plug in something for y. What am I going to plug in?
-6.
They gave me a y point. So I'm going to plug -6 into y because all I want is one variable missing. You get what I'm saying? I need an a or whatever, okay? So I'm going to plug in -6. So if I plug in a -6 equals a, x plus 4, x
Are
minus
you okay,
1,
sir?
x minus
Okay.
3. Okay, now here's the deal. What point went with that -6? 0. What do you think we're gonna do with that?
Put it in.
Plug it in for X.
Yes, so I'm gonna plug that in for x. 0 plus 4, 0 minus 1, and 0 minus 3. This way I can solve for a now, so that I will know what my a is, what my scale factor is, okay? So I have 4 times -1 times -3. What's 4 times -1 times -3?
Negative 12.
No,
12.
12. So then I get
Attaboy.
-6 equals
Negative.
12a. So what does a equal?
2. -2.
No,
Wait, what?
Yeah,
yeah, -1/2.
that's stupid.
-1/2. Okay, not done, because that's not an equation, that's just the a part.
Plug it in.
Okay, so, kind of, yes. So now, to get my equation, all I have to do is this. F of x equals -1/2 times x plus 4 times x minus 1 times x minus 3.
I'm a genius. Oh my goodness.
Oh, I'm dumb.
I don't mean to gloat, but I'm Albert Einstein.
Okay,
I'm the black Einstein.
and you can
They call
stop
me
there,
D.
you
Albert.
create an equation.
Devontae Einstein.
Yeah, he didn't do
That sounds like a basketball player on 2K. Devontae Einstein.
That sounds like
Okay, can you handle that?
my player story.
Yeah.
That shouldn't be too bad, okay? That shouldn't be too bad. They should always give you a point that has a y, a crossing through the y so that you can solve,
You're right.
okay?
You can advise. You can advise.
I still got that.
Okay, there's like
video
two more
That's
things,
when we
3
met
more things we have to
Mr.
talk
Lewis.
about.
Blaze him.
Okay,
Bruh, that was terrible.
so then we come to something called finite differences,
We talked about finite things in econ.
okay? So we found a function given its graph. Functions can also be written from a set of data using finite differences, okay? When the x values in the data set are equally spaced, the differences of consecutive y values are called finite. So what they're saying is it follows a pattern. They're equally distant from each other. If the x's are equally distant, then the y's follow this pattern called finite differences, okay? Some finite differences for the function f of x equals x squared are shown. So when you plug in a 1, you would get a 3 out, okay? When you plug in a 2, okay, we get like a 4. Plug in a 3, 9, plug in a 4, 16. Because I'm squaring them, yes? Because my function is x squared. There's a pattern there, okay? What that means is, if I take 4 minus 1, I have 3. If I take 9 minus 4, I have,
5,
if I take 16 minus 9, I get,
7.
those are the finite differences. The differences between the gaps of each segment.
And if you take 1 minus 4, you get negative 3. 4 minus 9. Oh.
So the finite differences above are called first order differences, okay? You can also calculate higher order differences, which we'll talk about in a second, but these are called first order differences.
Does that say the differences of consecutive y values or constant?
Bro, I'm so hungry right
Of consecutive y values, yes,
What they have for lunch?
okay?
Better be a
So
snack.
you are finding patterns in things, okay,
That's mine.
with finite differences. So here's another example of this, okay? The first 5 triangular numbers are shown below. A formula for the nth triangular number is f of n equals 1/2 n squared plus n. Show that this function has constant second order differences. So what we just talked about was first order. We're going to talk about what second order differences are, okay? So here's the deal. The n is simply the number I'm plugging in. So when it says f of n, that means when I plugged 1 in here to the n's, I got
0.5.
1 out.
Oh,
Okay.
you do.
Because 1 squared is
1 plus 1.
plus 1, which is
2.
2.
Oh.
2 times a half is
Crap.
1. When you plug 2 in, 2 squared is 4. 4 plus 2 is 6. 6 times a
3.
half is 3. Do you see how they're doing that?
Yeah.
Okay. So, I've got to figure out what the second order is, what's going on there. What that means is this. Let's figure this out. What's the difference between 1 and 3?
2.
What about 3 and 6?
3,
What about 6 and 10?
4,
And 10 and 15?
5.
5.
Okay. 2, 3, 4, 5, right?
Yeah.
Okay. what is the difference between this right here?
One,
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 one.
one.
Okay, so when you get to the same number, that's when you know you've gotten to where you need to be.
0, 0.
Okay, so what happens is this. The first several triangular numbers, or the first ones that we looked at, find the first order differences by subtracting consecutive triangular numbers. Then you find the second order differences by subtracting the consecutive first order differences. So when it says find the second order differences, you just have to simply subtract the first order ones and then subtract the second order ones to get to where you're at. And so on and so forth, that they ask you to find stuff higher than that. Which we're not gonna do anything higher, I don't think, than third order differences. Okay, properties of finite differences. So in the example we just looked at, the function has a degree 2, and that the second order differences are constant. That illustrates the first of the following two properties here, okay? Properties of finite differences. If a polynomial function f of x has a degree n, then the nth order differences of function values are equally spaced x values are non-zero and constant. So what they're saying is if I have a degree that's 5, I won't get to first order until I break it down to the fourth row. Okay? Because 5 minus 1 is 1. And then the converse of that statement is also stated. So then we get something like this. Okay. The first 7 triangular pyramid numbers are shown below. Find a polynomial function that gives the nth triangular, whatever that word is, number. Okay. So I want to figure out what this function is. Okay. So you know that when you plug a 1 in, we get a 1 out, right? When we plug a 2 in, we get a 4 out. When we plug a 3 in, we get 10, 4, 25, 35, 6, 56, 7, 84. Okay? I want to find the polynomial function, okay, of this. So here's what we get to do. This becomes really fun. First, we need to break this down until we get to all the same numbers. So we need to see what power it is. So what's the difference between 1 and 4? Between 4 and 10? 6 and 20? 20 and 35? This, what is it? 19? No. 21, yeah. And the difference between that?
I don't even know, because I gotta keep it real with you.
28.
Thank you, G.
Okay. What's the difference between 3 and 6? 6 and 10? 10 and 15? This,
6,
and this.
7,
Good, we're getting closer. 3 and 4?
1,
4 and 5?
1,
Beautiful.
1.
One.
Okay, so now I know that it should be, I know what type of power it should be, what type of, thing it should have, okay?
To the power of.
It should be a cube root, because we had to do 1, 2, 3 levels, okay, to get to all ones. Does that make sense? Okay, so I'm gonna have a cubic function. Because the third order differences are constant, you know that the numbers can be represented by a cubic function. Cubic functions look like this. There's something like y equals ax cubed plus bx squared plus cx plus d. Okay? Cube, square, x, constant. Okay? So you know you're looking for an equation along that line. This is where you're going to hate me. So now you need to take 4 separate equations and create this. Okay, we're going to create 4 separate equations. We're going to take that pattern, ax cubed plus bx squared plus cx plus d, and we're going to plug in this first function. I'm going to just take the first 4, 1, 2, 3, 4. Okay, I'm going to take the first 4 numbers and work with them. When you plug in this 1, you get a 1 out, right? So I'm going to represent this by saying 1 equals, I'm taking that equation there and plugging this in for that now. 1 equals, and you would have a times 1 cubed plus b times 1 squared. Do you get what I'm doing here? Okay? A
You have to
times,
write that for each one of them?
yeah.
That's stupid. Why would you do that?
that you're gonna use something called substitution or elimination here soon.
Right.
Hey.
Yeah.
But no.
Aesthetics for.
Isn't that the one that takes a long time?
I like small division, but it's close.
Actually, we want to leave, actually, we can't plug this
This is
in, there's
depression.
not an X there, I'm stupid. So we leave that as D.
D.
Okay. So if I broke this down, it would say 1 equals A plus B plus C plus D, right?
Yeah.
Okay, now, if I use the next equation for 2, I'm gonna say 2 equals, no, not 2, I'm gonna say 4 equals, because that's the outcome. 4 equals A times 2 squared cubed plus B times 2 squared plus C times 2 plus D. So if I break that down, I get 4 equals 8A, right? Oh, this should say squared. 4B, 2C, and then you get D. Okay? Now I have to do it 2 more times. I have to do it with 3 and with 4. Okay? So 3 equal, no, I keep doing that wrong, I'm stupid. 10 equals A times 3 cubed plus B times 3 squared plus C times 3 plus D, which would give me 10 equals 27A, 9B, 3C, D. Then I have to do it with 20 equals A times 4 cubed plus B times 4 squared plus B times 4 plus D.
Why do you need to do it 4 times?
Because I have A, B, C, and D. I need 4 equations.
Okay.
That's doing too much.
So then, if it was only a square function, then I would need 3 equations. Does that make sense? Okay. So then, 4 cubed, 64A, plus 16B, plus 4B, plus D. Okay, so now I have 1, 2, 3, and 4 equations, yes?
Is that it?
No.
See, that's, no, bro, come on.
Now I have to do substitution.
Actually, yes, we're gonna take it, well,
Yeah.
We can stop right there.
We'll stop right
The
there.
state
here's
don't
the
gotta
deal.
know.
We're gonna take it this far
Thank you.
because,
We ain't gonna do it.
we would need a graphing calculator to do it further than this. Because we can set it up into a matrix and solve on a graphing calculator with this, super simple. But we don't wanna do that. So if you can take it to this level for me, we're done.
I can do that.
Hallelujah.
That's pretty good.
The state didn't equip us well enough.
No, it's not.
Common Core is a joke.
What was that? What was the name of that?